A cruise ship can weigh 220,000 tons. That's heavier than 40,000 elephants stacked on top of each other. It's made of steel, which sinks like a rock when you toss it in water. So here's the question that should keep you up at night. Why doesn't it plummet straight to the ocean floor? And here's the really weird part. The bigger the ship gets, the easier it is to keep floating. A tiny metal coin sinks instantly, but a massive aircraft carrier the size of 3 football fields just sits there on the surface, like it's no big deal. That doesn't make any sense, right? Well, stick around, because the answer is going to completely change how you see the world around you. And trust me, the real reason has nothing to do with what you think. Before we get started, check out the link in the description to download our ebook. Today we're tackling one of the most mind-bending questions in physics: why massive ships don't sink. And I'm not just going to give you the textbook answer. We're going to dive deep into the actual mechanics, bust some myths, and by the end of this video, you'll understand something that most people never really grasp. This isn't just about ships, by the way. Once you understand this principle, you'll see it everywhere. Swimming pools, hot air balloons, even why you feel lighter in water. It all comes back to the same surprising phenomenon. So let's get into it. Alright, so here's where we start. Forget ships for a second. Let's talk about you. When you jump into a pool, you float, right? Or at least you can float if you take a deep breath and relax. But here's the question: why? Your body has bones, muscles, organs. You're solid matter. What's stopping you from sinking to the bottom? The answer is displacement. When you get in that pool, your body pushes water out of the way. It has to go somewhere, so it moves. And here's the key: that water doesn't want to move. It pushes back. This pushing back is called buoyant force, and it's the same force that keeps ships afloat. Every single object that enters water experiences this upward push. Always. No exceptions. Now here's where it gets interesting. The amount of push you get depends on how much water you displace. Push more water out of the way, get more pushback. It's that simple. And this is where the ancient Greek genius Archimedes comes in. Over 2,000 years ago, he figured out the exact rule. The buoyant force pushing up on an object equals the weight of the water that object displaces. This is called Archimedes' principle, and it's the reason everything floats or sinks. So if you displace 50 kilograms of water, you get an upward push equal to 50 kilograms of force. If you weigh less than 50 kilograms, you float. If you weigh more, you sink. It's a tug of war between your weight pulling down and the water pushing up. Now here's where ships get clever, and this is the part that blows most people's minds. Take a solid steel ball. Toss it in water. It sinks immediately, right? That steel ball might displace, let's say, 1 liter of water. 1 liter of water weighs about 1 kilogram, but that steel ball weighs way more than 1 kilogram because steel is about 8 times denser than water, so it sinks. Weight wins. But now, take that exact same steel and reshape it. Hammer it flat, bend it into a bowl shape, make it hollow. Suddenly, that same amount of steel can displace way more water. This is the secret. Ships aren't solid chunks of metal. They're hollow shells, giant floating bowls, essentially. And because they're hollow, they can displace an absolutely massive amount of water without weighing nearly as much. Let me give you a real example. The Oasis of the Seas is one of the largest cruise ships in the world. It weighs about 225,000 tons fully loaded. Sounds impossible to float, right? But here's the trick. That ship displaces about 225,000 tons of water. See what happened there? The weight and the displacement are equal. Perfect balance. It floats. And here's something wild. The ship doesn't need to displace water equal to the weight of all the steel. It needs to displace water equal to the total weight of everything. The steel, the fuel, the cargo, the passengers, the furniture, the swimming pools, everything. So ship designers calculate exactly how much volume they need to keep all that weight floating. They design the hull, that's the bottom part of the ship, to be big enough and deep enough to push aside the right amount of water. And as long as the ship weighs less than the water it displaces, it floats. Let's talk about density for a minute, because this is really what it all comes down to. Density is just how much stuff is packed into a space. Steel is dense. Pack a lot of mass into a small volume. Water is less dense. A ship, even though it's made of steel, has lots of empty space inside. Cabins, cargo holds, engine rooms, hallways, All that empty space means the average density of the entire ship is actually less than water. Think about it like this. Imagine you have a bottle. If it's solid plastic all the way through, it sinks. But if it's empty inside with a cap on, it floats. Same material, different density. The air inside lowers the average density of the whole thing. Ships work exactly the same way. Yes, steel is denser than water. But steel plus air is less dense than water, and that's why ships float. Here's another way to think about it. You know how a balloon floats in air? That's because the helium inside is less dense than the air around it. The air pushes up harder than the helium weighs, so up it goes. Ships are basically underwater balloons. They're less dense than the water around them, so the water pushes them up. And here's a fun fact that'll really drive this home. Modern cargo ships can be as tall as a 20-story building and as long as 4 city blocks. The EMA Maersk, one of the largest container ships, can carry 11,000 shipping containers. Fully loaded, it weighs over 170,000 tons. But because of its massive hollow hull, its average density is still less than seawater. So it floats. The Titanic, by the way, was designed the same way. It floated perfectly fine until water got inside the hull. Once water filled those compartments, the average density of the ship increased. More weight, same displacement. Eventually, it became denser than the water around it. Then it sank. And that brings us to something really important that most people get completely wrong about floating and sinking. Stay with me, because we're about to bust some myths that you've probably believed your whole life. Myth number 1. Bigger objects sink faster. Nope, size has nothing to do with it. Density does. A huge ship floats. A tiny pebble sinks. What matters is the object's density compared to water, not its size. In fact, and this is counterintuitive, bigger ships often float more icily, because as a ship gets bigger, its volume grows faster than its weight. Volume is 3-dimensional, so if you double the length, width, and height, you actually multiply the volume by 8. That means you can displace way more water without proportionally increasing weight. Engineers use this to their advantage. Myth number 2, metal always sinks. You've heard this one before. Metal is heavy, so it must sink. But we just proved that wrong. Metal sinks if it's solid, but shape it into a hollow vessel, and suddenly it's a boat. Same metal, different outcome. It's not about the material, it's about the overall density. Myth number 3, ships float because they're filled with air. Partially true, but misleading. Air helps lower the average density, yes, but the real magic is displacement. Even if you filled a ship partially with water, it would still float as long as the total weight remained less than the weight of water displaced by the hull. The shape and volume matter more than what's inside. And here's one more that surprises people. Ships don't float on the surface because water is holding them up from underneath. The force comes from all directions. Water pressure pushes on every part of the submerged hull. The upward force just happens to be stronger because pressure increases with depth. So the bottom of the hull experiences more upward push than the top experiences downward push. That difference is buoyancy. So let's bring this all together. Why don't big ships sink? It's not magic. It's not because they're special. It's because of 3 simple principles working together. 1. Displacement. Ships push water out of the way, and that water pushes back with a force equal to its weight. 2. Shape. Hollow hulls let ships displace massive amounts of water without being too heavy. 3. Density. As long as the average density of the ship is less than water, the buoyant force wins and the ship floats. The same steel that would sink as a bar floats as a ship because shape changes everything. And here's the mind-blowing part. This principle works everywhere. It's why icebergs float, even though ice is solid. It's why you float better in the ocean than a pool, because salt water is denser. It's why hot air balloons rise. Same physics, different applications. Next time you see a massive container ship on the ocean, remember, it's not defying physics. It's using physics perfectly. Those engineers aren't fighting nature, they're dancing with it. And here's your final takeaway to think about. The reason ships float is the same reason you exist. Seriously, your lungs are full of air, lowering your body's average density just enough that you can swim. Evolution gave you built-in buoyancy control. You're basically a biological ship. Pretty cool, right? If this video changed how you see the world, hit that like button. Subscribe if you want more mind-bending. Science explained simply. and drop a comment telling me what everyday phenomenon you want me to explain next. Thanks for watching, and I'll see you in the next one.